Hi folks, the point of this video is to introduce you to Euler's formula, one of the more interesting and vital formulas we're going to run across in differential equations. Euler's formula is simply this: e to the ix power equals cosine of x plus I times sine of x, where I is the imaginary unit, I equals the square root of -1. So this relates complex exponentials with the circular trig functions. It's worth a minute of our time to review the powers of I. I to the 0 power is equal to 1. I to the first power is I. I squared, well, that's defined to be -1. I cubed can be broken up into I squared times I, which is -1 times I, which is the opposite of I. I to the fourth can be written as I squared times I squared, which is -1 times -1, which is 1. And from this point on, the cycle repeats. Once you get I to the fourth equals 1, the powers of I repeat themselves in steps of 4. So there's I, -1, -I, 1, I, -1, -I, 1, etc. Let's think back to everyone's favorite topic in Calc 2, power series. What was the power series expansion for e to the x? Centered at 0, it was the summation n equals 0 to infinity x to the n over n factorial. In Calc 2, we were concerned with real numbers x, and you can show using the ratio test that for any real number x, this series converges absolutely. It turns out this formula is how we define the exponential function for not only real numbers, but complex numbers as well. And it turns out that you can show, using some advanced mathematics, that this series converges absolutely for any complex number. Let's take this series and substitute I times x. That's the series n equals 0 to infinity, I times x to the n power over n factorial. And I'm going to break it up into the evens and the odds because I'm thinking ahead here. Let's look at n equals 0. Well, any number to the 0 power, including 0 in this convention, is 1. 0 factorial is 1. So the 0th term is 1. I substitute n equals 1. I get ix to the first power over 1 factorial. And I'm going to write that as I times x. Let's look at n equals 2. I've got I squared, which is the -1, x squared over 2 factorial. I'm going to write that as minus x squared over 2. Substitute n equals 3, I get I cubed, which is the opposite of I, times x cubed over 3 factorial, which I'll write as the opposite of I, x cubed over 6. The n equals 4 case, I get I to the fourth, which is 1, x to the fourth over 4 factorial. So that's going to give me a positive x to the fourth over 24. What about n equals 5? I to the fifth power, well, I'm starting to repeat the powers of I again. That's going to just be I, x to the fifth over 120. Now, as you can see, when n is even, I'm getting real number coefficients because all the even powers of I are either plus or minus 1. With the odd exponents, the odd n's, I'm getting a factor of I each time. So what does that allow me to do? It allows me to break up the sum n equals 0 to infinity I x to the n over n factorial into two parts. There's the real part, 1 minus x squared over 2 plus x to the 4th over 24, etc., plus the imaginary part, x minus x cubed over 6 plus x to the 5th over 120, etc. Why am I allowed to rearrange terms and factor things out? Well, it's because of this theorem from complex analysis, which says that this power series converges absolutely. And absolute convergence allows me to rearrange terms and factor things out and not have to worry that it's going to add up to something different. These two series are famous enough. They're things that you should know from Calc 2. This is the series for cosine, and this is the series for sine. The first interesting consequence happens if we let x equals pi. I get e to the I pi is cosine pi plus I sine pi. So e to the I pi is the cosine of pi, -1. The sine of pi is 0. Or I could rewrite this formula, e to the I pi plus 1 equals 0. This is one of the coolest formulas in mathematics because it involves the 5 fundamental constants of mathematics, e, I, pi, 1, and 0, and the fundamental operations of mathematics, multiplication, exponentiation, and addition. But wait, there's more. E to the ix is cosine x plus I sine x. What's e to the negative ix? I can think of that as e to the I times negative x, which is cosine negative x plus I sine negative x. Using the even-odd properties of cosine of negative x is just cosine x, sine of negative x is minus sine x. So some interesting things happen when we use these two formulas. Let's write them right underneath each other. Come on, you know you want to do it. Let's add them up. E to the ix plus e to the negative ix equals what? The cosines add up, the I sines cancel out. That means that the cosine of x is equal to e to the ix plus e to the negative ix over 2. Now, doesn't that look familiar? This is the same form the cosh, the hyperbolic cosine, looked like. So now we get this nice little relation. The cosh of ix is the cosine of x. Remember when we talked about the hyperbolic functions and how similar they were to the trig functions? Well, this is why. I'll leave it to you, using similar hijinks. You can show that the sine of x is e to the ix minus e to the negative ix over 2I, which means that the sinh of ix is I times the sine of x. And so there's our discussion on Euler's magical formula. We'll be seeing a lot of him here in the next week or so. Thank you.